My name is Dr. Mike Murphy. I'm an assistant professor of computer science and information systems at Coastal Carolina University. In this lecture, I will introduce dynamic memory allocation at the system level. This method of memory allocation improves the degree of multiprogramming that a system can provide by allocating memory to processes as needed instead of ahead of time in fixed-size chunks. Fixed memory partitioning is fast and efficient in terms of overhead, but it wastes space and limits the number of concurrent processes to the number of partitions that will fit into RAM. Dynamic memory allocation resolves this issue by allocating memory to processes as it is needed. This mechanism increases the degree of multiprogramming that the kernel can support, but this improvement comes at a cost of greater complexity. In addition, there are trade-offs present in dynamic memory allocation that directly affect the performance of the system. These issues include efficiency, methods for tracking free space, algorithms for determining where to make the next allocation, and memory fragmentation. The primary issue with dynamic memory allocation is fragmentation. During execution, processes allocate and free memory in chunks of varying sizes. Over time, regions of free space within memory become non-contiguous, with sections of allocated memory in between sections of available memory. This fragmentation could lead to serious performance issues, since program execution speed will drop dramatically if every data structure must be implemented as a linked list of small pieces. Furthermore, algorithms that try to perform on-the-fly memory defragmentation are extremely complex to implement and would also severely impact system performance. Since it is impractical to avoid or fix fragmentation, memory fragments are a significant concern when space is dynamically allocated. Small fragments of memory are useless to programs, particularly C and C++ programs, which require structures and objects to be allocated in contiguous memory regions. These structures are likely to be in various sizes that are not efficient to utilize for memory management purposes, so the systems will allocate a few more bytes than the structures actually require in order to improve efficiency of the memory tracking systems. Furthermore, structures and objects will be allocated and freed numerous times during program execution, further fragmenting the RAM. Over time, fragmentation can waste large portions of the system memory, limiting the degree of multiprogramming by making it impossible for new processes to start. There are two types of fragmentation, external and internal. External fragmentation occurs when free space in memory is broken into small pieces. Over time, as blocks of memory are allocated and deallocated, this type of fragmentation tends to become worse. External fragmentation is so bad with some allocation algorithms that for every n blocks of memory that are allocated to a process, the system wastes another half n blocks in fragments. With these algorithms, up to a third of system memory becomes unusable. The other type of fragmentation is called internal fragmentation. Internal fragmentation occurs because memory is normally allocated to processes in some fixed block size. The block size is normally a power of 2 in order to make the kernel memory tracking structures more efficient. Processes tend to request pieces of memory in sizes that do not fit neatly into these blocks. Thus, it is often the case that parts of a block are wasted as a result. For small memory requests, large portions of the block may be wasted. When a process requests heap memory, the kernel must find a chunk of free space large enough to accommodate the request. This chunk cannot be smaller than the requested size, since the process expects to use all the space it is requesting. Since the memory is divided into blocks for efficiency, the chunk of memory returned to the process is normally larger than the amount requested, unless the process happens to request a whole number multiple of the block size. I'm now going to introduce 4 classical algorithms for dynamic memory allocation: best fit, worst fit, first fit, and next fit. The first classic algorithm for dynamic memory allocation is the best fit algorithm. In this algorithm, the kernel searches for the smallest chunk of free space that is big enough to accommodate the memory request. Although best fit minimizes internal fragmentation by avoiding over-allocation, external fragmentation is a major problem. An attempt to reduce the external fragmentation in the best fit algorithm is observed in the somewhat counterintuitive worst fit algorithm. Using the worst fit algorithm, the kernel finds and allocates the largest available chunk of free space, provided it is large enough to accommodate the request. In theory, this allocation strategy leaves larger, and thus potentially more usable, chunks of free space available. In practice, however, this algorithm still fragments badly, both internally and externally. Aside from the fragmentation, both of these algorithms are impractical in actual kernel implementations because they must perform a search of the entire free list to find the smallest or largest chunk of memory. The need to search the free list is eliminated using the first fit or next fit algorithm. In the first fit algorithm, the kernel simply finds and allocates the first chunk of memory that is large enough to satisfy the requests. This approach does result in internal fragmentation, and it also tends to create small fragments of free space that accumulate at the start of the free list, reducing performance over time. The next fit algorithm avoids the external fragment accumulation by starting the search for the next chunk of memory from the most recent allocation. In practice, only the first fit algorithm is used in the Linux kernel, and then only for embedded devices. This algorithm is called the SLOB allocator, which stands for Simple List of Blocks. For non-embedded systems that have the computational power for a more complex algorithm, SLAB allocation is used instead of any of these simple algorithms.